In Frank Herbert's Dune series, there is a popular saying, he or she who controls the spice controls the universe. And this proposition seems so temptingly simple. Control the spice, control the universe. It's kind of like in the Heroes TV series from a few years ago, save the cheerleader, save the world. Is it really that simple? Not exactly. See, in the fine print is how you're going to do that and what it's going to cost you to get there. So this is a story of sustainability, observability, and striking the balance between the two. I'm Nicole van der Hoeven. I'm a senior developer advocate at Grafana Labs, which pretty much means that I learn how to do things in public. And this is one of those things. I wouldn't call myself a tree hugger, far from it. What I am is a sci-fi buff, and I really, really love Dune. Keep your devices with you because we're gonna do some things later. Don't worry, you don't have to talk to anybody. You will play a game on your own, and we will see how to load test this application. Okay. So I told you I'm a sci-fi buff. When I say I love Dune, I mean I still today recite the litany against fear the way some people would a prayer. But I'm going to not assume that you are like that, and I'm going to show you a little, I'm going to explain to you what this rich world is. So in the Dune universe, there's one thing that you have to know about, and that's the spice. Spice underpins everything. Spice is this golden orange colored powder that is highly addictive and very potent. And it is the single most important thing you need to know about this universe. So on the top left there, that is the Spacing Guild Navigator tank. And they actually ingest a form of vaporized spice. Without that spice, they can't fold space. And they can't see through the different time continuums to be able to select the right one. So in this universe, spice enables space travel. In the bottom left, that is one of the Bene Gesserit. The Bene Gesserit are like they pretend to be a religious faction, which they kind of are, but actually they're really political. And what they use spice for is prescience. With spice, you can predict the future, which is not really the sort of thing you would want in the hands of politicians, but there you go. That's why they have to pretend they're religion. At the bottom in the center there, that's a mentat. In this universe, thinking machines aren't allowed. That's another whole other talk that I could give, but they use spice to heighten their senses and to be able to focus on the things that they need to focus on. They're kind of like human computers. At the upper right, that is a Fremen. I think that's Zendaya, but also pretending to be a Fremen. And she is, the Fremen in this universe are the people that cultivate the spice. They produce the spice. It is, to them, the economic resource that they need to protect. It causes them to be important in the grand scheme of things. It also has religious, ritualistic significance for them. And then at the bottom right, well, spice is a drug. Spice melange is also highly addictive. It causes heightened states, and people really use it recreationally as well. So in this universe, spice powers a whole lot of things. Not all of them good, some of them evil, just like any other resource. Spice is also only found on one planet, which is why it's so expensive. It's found on this planet, which is not Mars. It is Arrakis, also called Dune. Spice is found on this planet only because this is a desert planet, and on this planet, these creatures called sandworms exist. So the Fremen are the native inhabitants of this world. The spice is theirs, or at least it was before other people came to decide that it was theirs. In fact, spice only exists because of these sandworms. This is an example of a sandworm, and this is like, imagine this to be hundreds of meters long. These are gargantuan, like Leviathan sandworms that go up onto the surface. And aside from being really scary and eating pretty much anything, like humans, machines, vegetation, they also are pivotal to the formation of spice. Spice doesn't exist without sandworms because in the life cycle of a sandworm, all throughout the stages, it's cultivating spice in some way. So when it's in the larval form as a sand trout, the sand trout actually secrete the substance that sequesters the spice away from water. And then all the way up to becoming an adult sandworm, aside from eating any potential prey, a predator that could eat the spice, including humans, the sandworms also burrow in the sand and distribute the spice and the sand trout across the layers of sand. So spice doesn't exist without sandworms, but sandworms also don't exist in the presence of too much water. That's a problem because Fremens are still humans. The people that live on this planet need water to survive, but the existence of the planet, economically, politically, socially, only exists because of spice. So the Fremen have to live with this tension. They have to cultivate water because they want to survive, but they also want to cultivate spice. So there's this balancing act that they have to do that they don't always get right. And we have to deal with that tension all the time too. So the way that I think of it is in our world, spice is telemetry. Spice is data. That could be logs, metrics, traces, and continuous profiles. And telemetry is important. It is what we use to maintain our systems. It is how we know where things are, what's happening. When something goes wrong, the telemetry is what we need to check it. It's how we know that we're fulfilling our obligations to our customers. It's how we know that we're still within our SLOs. It's what drives business decisions. So telemetry is important. On the other side, we sort of vaguely know as engineers that all of this costs. Maybe not us specifically, but it costs someone. It costs the company. And in general terms, the water is energy. So that could be our time or our effort, but it could also be the cost to the environment. And we kind of abstract that away. We know that sometime, somewhere, it costs the environment. But since we don't see the data centers, I can't remember the last time that I ran code in a server that I actually saw physically. So it's all very removed. So how do we find out what that cost is? Well, with the Fremen, they are able to tread this balance very carefully. Top left, Zendaya again, looking very much like how a Fremen would not look, but the movie producers paid for that face, so she has to show it. A Fremen would never be barefaced in the open desert. She's wearing a still suit, which if you attended the keynote, sounds like the biosuit that the keynote speaker was talking about. A still suit is like a technical bit of clothing that retains the moisture of the body. It's kind of gross. Just don't think about it too much, but everything that the body secretes, it kind of stores and then recycles. That's how much it's important to them to maintain their water discipline, that even the body liquid that they exude, they have to think about recycling that. Bottom left is what's called a wind catcher, and they deploy those near their villages, which are called sieges, and it traps trace moisture in the air, again, to be recycled. And when they have the water, they put them in these like communal pools in their sieges. That's the upper right. And it is so important that stealing water is more dangerous, a bigger sin than actually stealing someone's life. It is said in Fremen culture that the flesh belongs to the man or person, but the water belongs to the tribe. That's how they think of water. And yet we also see these weird customs like the bottom right. which is like a shocking, very uncharacteristically Fremen waste of water. They have these rituals. This is the water of life. And in this ritual, they take water and they drown a young sandworm in it. And this is like, to think that water is so important to the Fremen, and so is the spice, and for them to mix the two for pleasure, for togetherness, is unheard of. But this is so important to them. This is a very ritualistic ceremony, almost, where the entire siege participates and they feel really at one with each other. Because remember, spice really enhances the senses and increases prescience. So I just want to go over a few terms. Energy is, so you think about a car. Energy is how much fuel is in the tank. But power is the rate, how fast that fuel is being burned up. I'm mostly going to be talking about energy here. And when we talk about trying to quantify the cost of what we're doing, this is the number that I got. 18,638 terawatt hours is used by data centers every year. Now, that's not observability, that's not cloud computing, there's a lot of like asterisks here. But just to give you perspective, if we had an electric vehicle that could do this, we could drive to the moon and back 750,000 times. That's what that powers. That's how much we are consuming as a whole. This is how much our data centers are costing. But that's not actually the cost to the environment, that's still just energy. So what we can do is we can take the energy output or consumption and then try to translate that into what is a direct environmental cost. And you've probably heard of this. It's carbon dioxide emissions. So all that this equation means is that if you want to find out how much you're emitting in terms of carbon dioxide, you take the energy usage and then you multiply it by some magical number. The CF is called the carbon coefficient or emissions factor or carbon intensity. It's all the same thing. And this factor can be one of many things. Primarily, it is the source of energy. So this is the primary determinant of the carbon intensity figure, whether it was wind energy or solar or coal powered. But there are also other things like conversion efficiency, how easy it is to convert one kind of power to another, or transmission efficiency. How do you get this power to the consumer's hands? And then there are also things that are kind of incidental costs, even like a zero carbon plant isn't really zero carbon when you think of all the trucks that were used to build, to bring the materials that were used to build that plant. So all of this factors into the carbon coefficient. Now, this is a map that AWS and GCP both use. This is the map of the carbon intensity across the world. This is electricity maps. So we're trying to approximate how to quantify what we're doing, how much what we're doing costs. And here you can see that the redder ones, the darker colors, are the ones that have very high carbon intensity, meaning they probably don't use a clean source of energy. And then the lighter green ones, the kind of yellow-green ones, are the ones that have low carbon intensities, using clean water or very efficient grids. On top of this, though, there's another layer, and it just gets so complicated. Because, for example, this is the carbon data across Google Data Cloud regions. And maybe you can't see all of it, but the fourth column is the carbon intensity. But the third column is this new thing that they're doing, which is Google CFE percentage, which is carbon-free energy percentage. See, on top of the electricity that really is set by the country, Google adds this other layer of complexity where they can decide, because they're such a big player, to purchase their energy, not from where everybody else, where consumers in that country would purchase energy from, but they could say, actually, we're going to pick this solar energy or something. That's what we're going to use for our data centers. So you also have to take that into account. So for example, there's one here. I was happy to see Iowa is where I chose to put my Kubernetes cluster, and I was scared that it was 413, the carbon intensity, so high is bad. So it's not very good for carbon intensity, but I was happy that Google's carbon-free energy percentage for that region is 87%. They purchase a lot of wind energy from wind farms in Iowa, so they don't actually go to the normal grid. So in general, that's still pretty good. 87% of the energy that Google consumes from that region is carbon-free. Still really complicated, right? So I'm going to show you what we can do, because there's no way that you're going to keep all of that in mind when you're deploying software. At least I know I can't. Now I'm going to do a demo, so let's see how that goes. Well, first, what should I show you? I'm going to show you, actually, I'll show you first this dashboard that I have. Oh, you know what? I'm first going to show the architectural diagram. All right, so I built this app. It is super simple, just for the purposes of this talk. It is a game, and it's a front-end game, and it runs entirely on the front end. And it is an Engine X, and it also is instrumented with Faro. I tried OpenTelemetry, but I found Faro was better. So Faro is a web SDK for instrumenting the front end. So with Faro, I can use it to kind of get these front-end metrics. I'm going to show you that in a bit. Now, that Nginx server is running on a pod called Spice Runner, and in that pod is also an Nginx exporter that takes metrics that are Nginx specific, and I'm also using Alloy to instrument it. Alloy is a flavor of the OpenTelemetry collector, so it's just getting a lot of telemetry and then sending it further down. Now, I'm using this thing called KEDA, which is a CNCF tool. By the way, all of the tools I'm mentioning are open source and free. I'm not using any SaaS platforms here. KEDA is something that it is for auto-scaling. It scales pods. So what it does is it tries to determine whether it needs to create another pod. So potentially, like if I run a load test, right now my testing tool is K6, but we're not going to use it. We're going to use all of you, hopefully. If KEDA detects that it needs another pod to handle the requests, it will create another pod. So then the telemetry is communicated to these databases, Loki, Tempo, and Prometheus, for logs, traces, and metrics. They all have persistent volumes attached to them. And then that is then visualized in Grafana. And what I found in the process of doing this is when you run a load test, you also should scale Grafana, because it became a bottleneck as well, because I was generating so much data that it was very difficult. It took too long to visualize it for my liking. All of this is running in GCP, and I am also using the GCP GKE cluster autoscaler. So this one scales across nodes. KEDA scales pods, and then the autoscaler, the cluster autoscaler, scales nodes. It will create a new node and then let Kubernetes schedule the pods accordingly. So this is the whole thing that I'm building, but now let me show you the actual app, because I think it's pretty fun. Oh, here's a cool Grafana dashboard. And I'll go through this a bit later, but there are currently 2 pods and 5 nodes. It's just a pretty simple game. If you've seen that Chrome Dino game, it's pretty much that, except I reskinned it, so you're a Fremen instead running through the desert, and you're dodging these sandworms. Oh man, it's hard to talk while I'm playing. I'm not going to get a good score, so don't judge me. But pretty much, every time someone plays that, you can also see these things on the console, or maybe you can't really see very well. But that is Faro sending telemetry back down the chain. Okay, so I'm going to show you the auto-scaling configurations. Okay, here is the KEDA manifest, and here's the important bit. One cool thing about KEDA is you can scale from 0. So here's the one for the pods. The min replica count for the pods is actually 0. That's super cool about KEDA. You can actually scale to nothing. And it just means that there's going to be a cold start. You decide for your business case whether that makes sense to you, or maybe you always prime it with something, I don't know. And then I set the max replica count to 200. And then I have a check every 5 seconds because it checks a few conditions. And based on what those conditions, whether those conditions are met, it will increase the number of pods. And then if those conditions are no longer met after 30 seconds, it will start to remove the number of pods. So here are some of the conditions that it looks at. So one is it looks at the HTTP request rate, which it's getting from Prometheus. I've set it really low, just for the purposes of the demo. You would not actually do this in production, but I set it to 1. So one pod per 1 request. I know, shocking use of energy usage, but we will see what that does. The second one is CPU utilization. I've just set it to 50%. In reality, I'd probably set it to like 80%. That's more comfortable. And then this is also, I can set the same things for Grafana. Okay. The GCP one, the autoscaler, is also something that we should probably look at. And this is not set in a YAML file because it's set by GCP. So I set it through the CLI, but just so you know, here's what I've got it set to. I've set it to a minimum of 1 node, always need 1, and a max of 10. And then the things that it will look at is whether or not there are pods that are unschedulable. So if there are pods that are running already, and even if the utilization is high, but there are no pods that cannot be scheduled, then it's not going to create a new node. It's only when a pod needs to be scheduled and cannot be scheduled based on the resource limits that it will trigger the creation of a new node. And so, yeah, so if pods are also in pending state because there's not enough CPU or memory, then it will create a new node. And then this is some scale down conditions. All of this is configurable. This is just what I set. But now let's actually try it. Now what I wanted to do is I want to try and actually have you all test this, and let's see if it actually scales. So please have a look and play this game. And you can use the QR code or use this URL. And maybe we can watch it in real time as things scale up and maybe down. I'm going to switch to the cluster so that we can watch it. Okay, so already there are 5 pods. Oh, wow, that moved up to 10 really quickly. We're now at 6 nodes. 37 requests per second, 37 active game sessions. This is great. Hey, this is working really well. It's always a risk, you know, when you do a demo like this. Don't know if it's going to work. It looks like it is, but I also want to see people's scores. Yeah, I'm looking at your stuff. So this is another dashboard for app stats. I get all of the Nginx logs, high scores. That's not very high, people. Okay, I got pretty good at this when I was testing it. So I got up to 4,000. And you just get into this like flow state where you don't even see anything anymore. That's a lot of jumps and a lot of collisions. Okay. Now we're at 8 cluster nodes. So this is the beauty of it. When you have auto scaling turned on, I'm not manually trying to assign anything. I'm not manually trying to set the number of pods beforehand or the number of nodes, like why would I? What I do is I set resource limits. This is how much resources I'm willing to assign per pod. KEDA determines whether it needs a new pod. And then this is how big the nodes are. That is fixed by GCP or GKE. And then the autoscaler will determine whether I need a new node. And then when that new node is created, then Kubernetes will determine whether some pods will go to it or not. Which pods will go to it? Will it be a Grafana pod or an app pod? This is all determined on its own. And so this is really cool, because that means that, if I were thinking, like right now, I didn't know how many people would play. I didn't know how many people would come. So if I had to try to guess how many pods I should have up or how many nodes, I might have gone like 20 nodes, just in case, What would have happened to the extra 10 nodes? Well, that would have just been a waste, right? Because I'm thinking of making sure that this application is always available. And sometimes that leads me to, actually a lot of times, that leads us to overpredict demand so that we're at least ready for it. What autoscaling does is it helps us be a little bit more conservative while not sacrificing on the experience of users. So if 100 more people came here, this would just scale up to meet that demand. Whereas if I were trying to hard code this, then I would have never foreseen that. So this is really cool. That actually worked out pretty well. So now we can go through these things a little bit. And then maybe later we'll see this start to cool down. Or maybe people just keep playing it for the rest of the talk. So the game sessions per pod, we're aiming for 1-to-1. Right now it's at 0.5 per 1. So it's on the rise. I think CPU utilization is also quite high. And you can see there's still some pending pods. They're unschedulable. So we can expect that if I had not set the number of nodes, the max number of nodes to 10, this would probably be higher. But, I didn't want to spend an unlimited amount of my company's money. So I set it to 10. So I'm monitoring all of this in real time. And I can also see the pending pods over time has also increased. So none of these panels I actually did myself. This is just the Kubernetes monitoring dashboard had some Kubernetes monitoring Helm chart already had some pre-configured dashboards, and I'm lazy, so I just took them. Now, I'd also like to show you something called Kepler. So remember how I was saying that it's really difficult to keep everything in mind for, okay, this is how many pods I'm using, how does that translate to energy, and then how does that translate to carbon dioxide? You don't really have to. There's this cool thing called Kepler. It is experimental, so use at your own risk. It's not 100% accurate. If you are running your own hardware, then I think they said it's like up to 90% accurate for carbon dioxide emissions and energy. But if you are running in the cloud, like a lot of us are, then it's going to be about 80% accurate. But that's still a good starting point, right? The absolute number doesn't matter. I think the change in that number matters a lot more. So this is the manifest for Kepler, and I really didn't change anything except tell it where to get the metrics. Kepler uses eBPF, so it attaches to the kernel and gets a lot of metrics that way. And then it uses machine learning to kind of learn which activities, which Kubernetes workloads generate more or less energy. But you don't really have to know that. You install the thing, there's a Helm chart, and what you get is this pretty dashboard. So this is from the last 7 days, and yes, I'm aware of the irony of talking about environmental sustainability and then also using resources. I get it, but I'm hoping that maybe if more of us did this, then maybe we'll just be a little bit more intentional about our usage. But what's great about it is now I just know exactly how much power, how much energy I'm using, my estimated carbon dioxide emissions. I didn't have to calculate any of this. I didn't have to care about Google CFE percentage or look at the carbon intensity. I don't even really know that, but I have all of the information here, and it has not affected my daily operations, assuming that this is an actual thing that I would be doing. But this is all just calculated for me. It's also interesting to see which containers are actually taking up the most power. I would have thought that it would be like the actual app, which is spiced runner, but look, system processes actually takes up more. That's almost certainly not going to be the case for much more complicated applications than my little game. But yeah, Kepler is not, it's not something that I would hang my hat on. Like if you absolutely need to know for legal reasons or whatever, I think it is a good starting point, but you should, it is a good thing to like just get the message out there that, hey, what we're doing costs as well, and here's how much. And if you use Kepler all the time, then you can use that to track how that number changes. So let's go back to the presentation here. Okay. So there's a lot that I talked about, but I'm going to also talk about the things that I didn't get to show you because I mainly showed autoscaling and Kepler. But here is a nice handy acronym for you, SPICE. So these are things that you can do to improve your emissions. And the first one is simplify. The number one thing really that you can do is only collect what you need. Don't start that compute if you don't need it. But also, if you're logging, for example, maybe you don't need those debug logs in production and maybe you should turn that off. All of that costs, but it doesn't do anything for your bottom line in terms of customer satisfaction. They don't see that. So those are the things that you want to trim. If you don't need them, then why are you doing it? You can also purify, you can drop unnecessary data. So an example of this would be like data retention. So if you need a high granularity of data for the last year, do you really need that for the last 10? Maybe you don't. Maybe you can stand a little fuzziness and maybe you can just start aggregating. So one of the things that I'm doing is on the telemetry collector level in Alloy, I'm actually aggregating some metrics. It's the one for like number of jumps. I don't really need every single jump logged. I just wanted like a general number of jumps or a number of collisions. So that doesn't get passed on further. I just graph and I track the total number and that just increments. So that also saves on costs. You can intensify, that's what I was talking about with the intensifying. Conserve, you can auto scale up and down. Oh, actually, let's see if that has scaled down now. It might be that it still takes a while if people play it, but you can already see that there is a dip, see? That is the number of pods that are being run. So it is going down. There's no longer any unschedulable pods. So see, it does scale down as well as up. And something like KEDA is going to scale down to 0 if you need to. So auto scaling really matters there. And then also evolve, because this sort of thing is really a cultural thing. People need to understand why you're doing it, and not everybody does. And you can't really change a culture overnight, but I'll tell you what, having a single source of truth and having a dashboard and everyone looking at that dashboard does a lot for moving the needle. It gets everybody on the same page and it's like a common rallying point. So I think just measuring and just observing, don't worry about whether that number is exactly accurate or not, but just having that is enough to drive some change. If you take nothing else away, then these are the things that I would suggest. These are practical things that you can put into place already. One is auto-scaling, which is why that's what I showed you. You can use pod and cluster one. Cluster level is probably going to be the one that's going to give you the most bang for your buck. So you could use, if you're on AWS, you can use Carpenter. Internally, Grafana Labs switched from the Kubernetes cluster autoscaler to Carpenter, and we found that it cut idleness by 50%. But this demo is running on GCP, so I just use the GKE cluster autoscaler. So a lot of these cloud providers have their own cluster autoscalers already. So if you can do that, then you're already a lot of the way there. And then having something like KEDA, which is such a great tool. I'm not at all affiliated with it, but I really love it. It's really good for pod autoscaling. So both of those can, on their own, already do a lot to help with your emissions. And then cloud providers also have these carbon footprint reports. I didn't lodge the request in time to get access to the GCP one for this demo, otherwise I would have shown it. But I have seen those reports, and they will give you how much they estimate your carbon dioxide emissions to be. Just take it with a grain of salt. Remember, when you're getting something like this from a cloud provider, it's in their best interest to make that number low. So just think of that, not saying that they would say the wrong thing, but they do take into account, like, offsets that they do. So maybe you still spent it, but then they paid a little bit extra to offset. So it's just something to be aware of. But they're still, like Kepler, a really good place to start. So let's go back a little bit to Arrakis, to Dune. What a lot of people don't know is it actually started with this thing on the right, with something that looks like our planet. It's blue, it's watery, there are rivers, there are seas, there are lakes. And what happened was, over time, spice production became so important that it became a desert. What I love about the Dune series is it's not a cautionary tale of like, oh, look how much our greed has destroyed our planet. Because, a bit of a small spoiler for the series, actually at the end of the series, Dune goes from becoming a desert back to being a water planet. And it's also not in a, hey, look what we can do with the power of hope. No, it was actually really bad. They got their water, but at the cost of spice. Spice production completely stopped. Arrakis was no longer known for spice. The Fremen lost that foothold into the universe because otherwise a desert people like them would not otherwise have a say. And so if this is a cautionary tale, it's actually, the warning would be not to swing too much in either way, in either direction. Sometimes when you do that, when you're like, I'm going to optimize this at any cost, whether that's spice or water, you just end up messing everything up. So I think the lesson of the Fremen and of Arrakis and of Dune in general is one of balance. It's not that we should prioritize one over the other. It's that we should recognize that both of these are tensions that we must sit with. And in our cases, we need to balance the need for telemetry, the need for data, the need to have our systems up and running for our customers, with the need for the environment, to have an environment to live in. We need to be intentional about the decisions that we make. We need to at least know why we're making those decisions, and are these things important enough to risk what exactly? We need the figures to say, like, yes, this is an acceptable cost, or no, it isn't. So it's not so much about, like, let's stop everything and shut down all of the data centers. Let's just know what we're saying yes to. Let's just monitor everything and then have those decisions be from facts rather than from misplaced emotion. So I think the lesson here is the spice must flow, but so must the water. And it's only by having both of those in our minds that we can be ethical software engineers. Thank you. That is my talk, and I have my slides and my repository with all my code and everything that I've mentioned, links to everything and references that I've used in this link. I do have I'm just asking for some feedback, so I just have 2 questions, but then you can get it. No, it's just all anonymous. But thank you all for having me here today.